Today we will consider electromagnetic waves perpendicular to B0 vector. Consider the propagation of electromagnetic waves perpendicular to the direction of magnetic field B0 vector. In this case, K vector is perpendicular to B0 vector. For transverse waves, K vector is also perpendicular to E1 vector. We now have two cases. One is ordinary wave when E1 vector is parallel to B0 vector. In this case, we find the dispersion relation, which is omega square equal to omega p square plus c square k square. This was similar to that which was in the absence of B0. So here we have find no effect of magnetic field. So this wave is called the ordinary wave. Now we will consider the second case of extraordinary wave when E1 vector is perpendicular to B0 vector. If E1 vector is perpendicular to B0 vector, the electron motion will be affected by the magnetic field B0. In this case, we take B0 vector equal to B0 z cap. Magnetic field B0 vector is assumed in the direction of z axis. So we write B0 vector equal to B0 z cap. And E1 vector is taken as Ex x cap plus Ey y cap. Since E1 vector is perpendicular to B0 vector, B0 vector is along the direction of z axis. So we assume E1 vector in xy plane having x and y components as Ex and Ey. So E1 vector we write as Ex x cap plus Ey y cap, and K vector is Kx cap. K vector is assumed along the direction of x-axis. Now we have these two Maxwell's equations, Maxwell's third and fourth equations. Del cross E1 equal to minus B1 dot and C square del cross B1 equal to J1 upon epsilon 0 plus E1 dot. The time derivative of this is operate delta upon delta t before this equation. So we get B1 dot in place of B1, J1 dot in place of J1, and E1 double dot in place of E1 dot. So the time derivative of this equation, we get this equation C square del cross B1 dot equal to J1 dot upon epsilon 0 plus E1 double dot. Now taking the curl of equation 1, this is equation 1, del cross E1 equal to minus B1 dot. If we take the curl of this equation, put del cross before left hand side and right hand side of equation 1. Curl means del cross. So we have del cross E1 equal to minus del cross B1 dot. And then we put the value of del cross B1 dot in right hand side. From this relation, C square del cross B1 dot equal to J1 dot upon epsilon 0 plus E1 double dot. So in right hand side we put the value of del cross B1 dot in the previous equation, and the left hand side, in left hand side we have del cross E1. So we use the formula A vector cross B vector cross C vector, which is A vector dot C vector times B vector minus A vector dot B vector times C vector. So this gives A vector dot C vector means del vector dot E1 vector, and then we have times B vector, and B vector is del vector, which we write before del dot E1. So we have del of del dot E1, and then we have minus A dot B times C. A dot B is del dot del, which is del square. So we have minus del square E1 vector. And in right hand side we have minus del cross B1 dot, and put the value of del cross B1 dot from this previous equation, dividing it by C square. We have in right hand side minus J1 dot upon C square epsilon 0 minus E1 double dot upon C square. Now assuming plane wave varying as e to the power I k vector dot r vector minus omega t, we have, if we assume a plane wave solution like this, e to the power I k vector dot r vector minus omega t, then partial differentiation with respect to t, delta upon delta t, will be equal to minus I omega, because in exponential with time t we have minus I omega. So delta upon delta t will be equal to minus I omega, and del vector is equal to I k vector. In del vector we have partial differentiations with respect to x, y and z, and here in exponential x, y, z are in r vector. R vector is x I cap plus y j cap plus z k cap. So del vector will be equal to I cap vector, which is with r vector. Now writing del vector as I k vector and delta upon delta t as minus I omega, we can write this equation as, put del vector as I k vector. So we have I k vector, and inside the bracket we have I k vector dot E1 vector. I into I is I square, which is minus 1. So we have minus k vector times k vector dot E1 vector. And in second term we have minus del square. Del vector is I k vector. So del square is I square k square, which is minus k square. So second term will become plus k square E1 vector equal to, in right hand side we have J1 dot. Dot means delta upon delta t of J1, and delta upon delta t is minus I omega. So for dot, which is for partial differentiation with respect to t, we write minus I omega and get I omega J1 upon C square epsilon 0. Similarly, in the second term of right hand side we have E1 double dot. Double dot is 2 times differentiation with respect to t. Differentiation with respect to t, delta upon delta t is minus I omega. So 2 times differentiation, as we have double dot, E1 double dot. Double dot means 2 times differentiation. d2 by dt square. So 2 times differentiation d2 by dt square will give minus I omega into minus I omega, which is I square omega square, and I square is minus 1, so we have minus omega square. So for double dot we write minus omega square, and this second term in right hand side becomes omega square plus omega square upon c square E1. Now we have k vector dot E1 vector in first term of left hand side, k vector dot E1 vector, and this k vector dot E1 vector will be equal to kex, because k vector is along the direction of x-axis, k vector is kx cap, and E1 vector is ex x cap plus ey j cap. So this dot product k vector dot E1 vector is equal to kex. So the first term will become minus k square ex x cap. For k vector dot E1 vector we write kex, and for k vector we write kx cap. So this first term will become minus k square ex x cap. Then second term is plus k square E1 vector, and in right hand side we write these terms as it is. Now bring the term of E1 vector from right hand side to left hand side. Bring this term from right hand side having E1 vector. If we bring this term in left hand side, it will become we have omega square upon c square E1 vector. This is the term, second term of right hand side. Keep this term as it is and bring these two terms of E1 vector and ex x cap to right hand side. Then we have omega square upon c square E1 vector minus k square E1 vector plus k square ex x cap. We will have here plus k square ex x cap. Then this will be equal to minus I omega j1 upon c square epsilon 0. And value of j1 is minus n0 e ve1. It is the current density due to electrons, and j1 current density for electrons is minus n0 e ve1. n0 is number of electrons per unit volume, minus e is charge on electron, and ve1 is the velocity of electron. So for j1 we write minus n0 e ve1. It is the current density due to electrons. Now in two terms we have E1 vector. Take E1 vector common and we get we multiply this equation by c square also. Then take E1 vector common from first two terms and we get omega square minus c square k square with E1 vector. Then we have plus c square k square ex x cap. It is plus c square k square ex x cap in place of minus. Correct it. It is not minus c square k square ex x cap. It is plus c square k square ex x cap. Here also we have plus k square ex x cap, because this term minus k square ex cap is taken to right hand side, where it becomes plus k square ex x cap. So correct here, it is plus k square ex x cap, and also here it is also plus c square k square ex x cap. And right hand side we have I omega n0 e ve1 upon epsilon 0. We have multiplied by c square, so c square is cancelled out here in denominator. Now we have this relation, omega square minus c square k square into E1 vector. Then we have plus in place of minus. It is plus c square k square ex x cap equal to I omega n0 e ve1 upon epsilon 0. Now E1 vector is ex x cap plus ey y cap. Then from linearized equation of motion of electron, the equation of motion of electron is this: m delta v upon delta t. It is mass into acceleration. And for v, we write ve1. It is the velocity of electron, because we are writing equation of motion for electron. So in left hand side we have mass into acceleration. Acceleration is delta v upon delta t, and v is ve1, velocity of electron. And it is the force acting on electron, and force acting on electron due to electric field E1 and magnetic field B0 is given by minus E1. It is the force due to electric field E1, and minus E V cross B, which is VE1 vector cross B0 vector. It is due to magnetic field B0. So left hand side is mass into acceleration, which is force, and in right hand side it is the force due to electric field and magnetic fields. Charge of electron is minus E, so force due to electric field is minus E1, and force due to magnetic field B0 is minus E VE1 cross B0. Now we write minus I omega for delta upon delta t, and we have minus I omega m VE1 vector equal to minus E into E1 vector plus VE1 vector cross B0 vector. From this relation we can find the value of VE1 vector, which is minus IE upon m omega into E1 vector plus VE1 vector cross B0 vector. Now VE1 vector, we write it as Vx x cap plus Vy y cap plus Vz z cap. VE1 vector having three components, Vx, Vy and Vz. So VE1 vector is written as Vx x cap plus Vy y cap plus Vz z cap, and it is equal to minus IE upon m omega, and put the value of E1 vector. It is Ex x cap plus Ey y cap. Then we write the value of VE1 vector cross B vector. This cross product can be obtained by using a determinant. So find the value of determinant. In this determinant we write in first row x cap, y cap, z cap. These are the unit vectors. Then the three components of VE1 vector, which are Vx Vy Vz, and in the third row we have three components of B0 vector. Those are 0, 0, B0. B0 vector is along the direction of z-axis. So to find the value of V cross B, we make a determinant, and from that determinant we find the value of V cross B as Vy B0 x cap minus Vx B0 y cap. From this equation we can find the value of Vx and Vy. Vx is the x component of velocity. It is equal to the term with x cap in right hand side. So, and similarly for Vy, it is the value of y component. So Vy will be equal to this right hand side terms containing y cap. So we can find these two equations for Vx and Vy, comparing the coefficients of x cap and y cap in left hand side and right hand side. Now from these two equations we can find the values of Vx and Vy. In the first equation of Vx we have Vy, and in the second equation of Vy we have Vx. So from this second equation we write the value of Vy and put it into the first equation. Substituting the value of Vy from equation 6 into equation 5, we get from equation 6 it is for Vy, and this value of Vy we put in this equation 5 for Vx. Then Vx will be equal to minus IE upon m omega into Ex, plus here we put the value of Vy, which is minus IE upon m omega into Ey minus Vx B0, and we get the value of Vx as this. Multiply by minus I inside the bracket. Minus I is outside the bracket, take it into the bracket. So first term will become minus IEx inside the bracket, and the second term is minus I into minus I. It is plus I square, and I square is minus 1. So we have minus E upon m omega Vy minus Vx B0 and B0 also. So the second term inside the bracket becomes minus E B0 upon m omega into Ey minus Vx B0. Now this E B0 upon m is written as omega c. It is the cyclotron frequency of electron. So we write omega c for this term E B0 upon m, cyclotron frequency of electron, E B0 upon m. And second term inside the bracket becomes minus omega c upon omega into Ey minus Vx B0. Now open the bracket of the second term and we get these three terms inside the bracket, Vx equal to E upon m omega minus I Ex minus omega c upon omega Ey plus omega c upon omega Vx be 0. Now in left hand side we have Vx, and in right hand side we also have term of Vx, that is the last term. So we take this last term of Vx into left hand side. So left hand side will become Vx minus E upon m omega c upon omega Vx be 0. And now in right hand side we have only two terms, E upon m omega into minus I Ex minus omega c upon omega Ey. Take Vx common. So we have Vx into 1 minus and now again we have EB0 upon m. This term EB0 upon m, it is again omega c. So we have omega c square. Omega c is already, and put EB0 upon m as omega c. So we have Vx into 1 minus omega c square upon omega square. And in right hand side this term is same. So we can find the value of Vx. Bring this term of with Vx 1 minus omega c square upon omega square into right hand side. So Vx will become E upon m omega into minus I Ex minus omega c upon omega Ey into 1 minus omega c square upon omega square to the power minus 1. Similarly, we can find the value of Vy. Vy will be equal to E upon m omega minus I Ey plus omega c upon omega Ex into 1 minus omega c square upon omega square to the power minus 1. So we can find the value of Vy also, and if we look at the value of Vx, then to find the value of Vy we write in first term Ey in place of Ex, and in second term we write minus Ex in place of Ey. So in first term we write in place of Ex as Ey, and in second term in place of Ey we write minus Ex. Now separating equation 4 into x and y components using equations 7 and 8. These are the equations 7 and 8 which gives the value of Vx and Vy. These are equations 7 and 8. And separating equation 4 into x and y components. This is equation 4. Separate it into x and y components. Write E1 vector as equal to Ex x cap plus Ey y cap, and Ve1 vector equal to Vx x cap plus Vy y cap plus Vz z cap. Then if we separate x component, write Ex in place of E1 vector. Then we have omega square minus c square k square into Ex, and the next term is plus c square k square Ex x cap. So this second term, which is plus c square k square Ex x cap, it is cancelled out. From this term minus c square k square Ex x cap. So for x component we write omega square Ex. In left hand side only term is omega square Ex. Other two terms are cancelled out. in the last term of left hand side we have positive sign in place of minus sign. So if we separate x components, we find in left hand side only omega square ex, which is the first term. Second and third terms are cancelled out. And in right hand side we have I omega n0 e upon epsilon 0, and x component of VE1 is Vx. So we have omega square Ex equal to I omega n0 e Vx upon epsilon 0, and put the value of Vx from this relation. Vx is this given by equation 7. Put this value of Vx, and right hand side will be equal I n0 e square upon m epsilon 0 into I Ex plus omega c upon omega Ey into 1 minus omega c square upon omega square to the power minus 1. It is obtained if we put the value of Vx in right hand side from this relation 7. So x component of equation 4 gives omega square Ex equal to this thing, and now we write n0 e square upon m epsilon 0. The term with minus I outside the bracket is n0 e square upon m epsilon 0, and this is omega p square. Omega p is electron plasma frequency. Omega p electron plasma frequency is under root n0 e square upon m epsilon 0. So we write the term with minus I as omega p square, and inside the bracket we have I Ex plus omega c upon omega Ey into 1 minus omega c square upon omega square to the power minus 1. Now in left hand side we have omega square Ex. In right hand side we have a term of Ex. So put the two terms of Ex together to left hand side and take Ex common. So we have omega square and take this term 1 minus omega c square upon omega square to the power minus 1 into left hand side. It will become omega square into 1 minus omega c square upon omega square into Ex equal to omega p square Ex minus I omega p square omega c upon omega Ey. Now put these two terms of Ex together in left hand side, take Ex common. We have with Ex omega square into 1 minus omega c square upon omega square minus omega p square. And also keep the remaining term in left hand side. It will become plus I omega p square omega c upon omega Ey equal to 0. Now if we solve this equation, we have solve this bracket, we get omega square minus omega c square minus omega p square into Ex plus I omega p square omega c upon omega Ey equal to 0. Now we write this as omega square minus omega h square. So we write omega h square for omega c square plus omega p square. So this term inside the bracket, we write it as omega square minus omega h square. Omega h square is omega c square minus omega p square. We assume it as omega h square is assumed as omega c square plus omega p square. So the first term in the bracket will be omega square minus omega h square, and then Ex, and the second term is I omega p square omega c upon omega Ey equal to 0. Similarly, we can find the relation for y component. This equation we have obtained, equation 9. It is obtained by using the x component. If we use the y component of equation 4, if we take y component of this equation 4, we have omega square minus c square k square Ey. Y component of E1 vector is Ey, and it will be equal to I omega n0 E upon epsilon 0 Vx. Y component of Ve1 vector is Vy. So take y component of this relation, equation 4, and from that we can find this equation. This is the equation we obtained from y component of equation 4. Omega square minus c square k square Ey equal to I omega n0 E Vy upon epsilon 0, and put the value of Vy, simplify this relation, and we obtained this equation minus I omega p square omega c upon omega Ex plus omega square minus omega h square minus c square k square into 1 minus omega c square upon omega square Ey equal to 0. Now we get these two equations, equation 10 and equation 9. These two equations 9 and 10, this is equation 9 having two terms, one of Ex and other is Ey. Equation 9 is this. It contains in left hand side two terms of Ex and Ey, and similarly in equation 10, this is equation 10, here also we have two terms, one of Ex and the second of Ey. For non-trivial solution, determinant of coefficients of Ex and Ey should vanish. In these two equations 9 and 10, if we want to find non-trivial solution, then we must write the determinant of coefficient of Ex and Ey equal to 0. So make a determinant of coefficients of Ex and Ey of these two equations and put that equal to 0. From this relation we can find this equation. omega square minus omega h square into omega square minus omega h square minus c square k square into 1 minus omega c square upon omega square equal to I omega p square omega c upon omega I omega p square omega c upon omega. The right hand side will become I square is minus 1 and we have omega p square omega c upon omega 2 times. So we write it as omega p square omega c upon omega whole square. Now in left hand side the first term is omega square minus omega h square. This we put in right hand side in the denominator. Then this equation reduces to omega square minus omega h square minus c square k square into 1 minus omega c square upon omega square equal to omega p square omega c upon omega whole square upon omega square minus omega h square. Or c square k square into 1 minus omega c square upon omega square equal to. Bring this second term of left hand side, bring this term to right hand side, so it become positive. So we write plus c square k square into 1 minus omega c square upon omega square equal to, this is the first term of left hand side, omega square minus omega h square, and now this right hand side term we bring it into left hand side, so it becomes negative. Take omega square LCM in this term. We have c square k square into omega square minus omega c square upon omega square equal to omega square minus omega h square minus the remaining term is same. Now we divide by omega square minus omega c square, so that in left hand side we have c square k square upon omega square. Divide by omega square minus omega c square and we get this term in right hand side, dividing by omega square minus omega c square. Now c square k square upon omega square will become equal to omega square minus, right here the value of omega h square. Omega h square we assume as omega c square plus omega p square. So the first term in right hand side in numerator will become omega square minus omega c square minus omega p square. Other terms are same. Now we divide the numerator by omega square minus omega c square. It is in the denominator. We have omega square minus omega c square. So divide numerator and denominator by omega square minus omega c square. The first two terms are omega square minus omega c square. If we divide this by omega square minus omega c square, we get 1. So we have 1 minus omega p square, minus is taken common so that the second term become plus, and divide by omega square minus omega c square. Now this will become equal to 1 minus omega p square into omega square minus omega h square. In numerator we take LCM, which is omega square minus omega h square, and solve it. Then in next step we have 1 minus omega p square we multiply by omega square in numerator and denominator, so that this omega square in numerator in second term of numerator will cancel out. So multiply by omega square in numerator and denominator, we get this relation. So c square k square upon omega square now becomes equal to 1 minus omega p square upon omega square into omega square minus, right here put the value of omega h square, which is omega c square plus omega p square. Other terms are same. Now we have this equal to 1 minus omega p square upon omega square into omega square into omega square minus omega c square. Then we have minus omega square into omega p square plus omega p square omega c square. In numerator, the first term inside the bracket we have three terms, omega square minus omega c square minus omega p square. We put the first two terms together and the remaining third term we write separately and get this next step. And then we write it as equal to 1 minus omega p square upon omega square into omega square into omega square minus omega c square minus, then in numerator in these two terms we write omega p square common, so that minus omega p square common, so we have omega square minus omega c square with it. In this way we write omega square minus omega c square in the two terms of numerator and in the one term of denominator. Now take this omega square minus omega c square in numerator as common, which is common to both the two terms of numerator. Take common omega square minus omega c square. With this we have omega square minus omega p square. With omega square minus omega c square in numerator we have omega square minus omega p square, and in denominator we have omega square minus omega c square into omega square minus omega h square. Now this term omega square minus omega c square is cancelled out in numerator and denominator, and we get c square k square upon omega square equal to 1 minus omega p square upon omega square into omega square minus omega p square upon omega square minus omega h square. And we write left hand side as c square upon vp square. Vp is omega upon k, it is phase velocity omega upon k. So we write omega square upon k square in denominator and write it as Vp square. Then c square upon Vp square will be equal to 1 minus omega p square upon omega square into omega square minus omega p square upon omega square minus omega h square. This is the dispersive relation for the extraordinary wave. It is an electromagnetic wave which is partly transverse and partly longitudinal, which propagates perpendicular to B0 with E1 vector perpendicular to B0 vector.